In this lesson, we're going to cover several methods for estimating canopy bulk density. We will not cover any direct measurements in this lesson, as these are not often done in management or in research. Before we begin the lecture, I want to remind you that the term crown refers to individual trees, while the term canopy refers to a stand characteristic. Canopy base height is not well defined or easy to estimate for a stand. There have been many definitions used to estimate canopy base height, such as the average crown base height of the stand, the lowest 20th percentile of crown base heights in the stand, or the height at which a minimum bulk density occurs. In general, most definitions are based on Van Wagner's idea that the canopy base height is the lowest height above the ground at which there is sufficient canopy fuel to propagate fire. However, this definition is vague and does not adequately define how we should estimate this characteristic. Our estimate of canopy base heights will greatly impact our fire modeling results, which are used to help us design our fuel treatment projects as well as locate areas for treatment. We will use the ponderosa pine stand we used in our last lecture to go over each of these definitions and review how they differ. We will also look at a few other definitions that are commonly used. Remember that on this site we had 1/10 acre plot, which was used to represent the stand. To calculate the canopy base height using this method, we simply average the crown base heights. In this example, we get an average canopy base height of 4.2 meters. Another simple option to estimate the canopy base height is to use the lowest crown height to represent the stand. In this case, our lowest crown base height is 1.9 meters. Scott and Reinhardt, 2001, suggest that neither the average crown base height or the lowest crown base height are accurate estimates of the canopy base height, even though both of these estimates have been used in scientific literature. So let's explore a few more ways to estimate canopy base height. Another method that has been used in several studies is to estimate the canopy base height using the lowest 20th percentile crown base height for the stand. To do this, you need to put the crown base heights in order from the lowest to the highest. Here's what our data will look like. Next, we need to locate the 20th percentile to do this, and to do this, you multiply the number of samples, crown base heights, by 0.2. This number tells you which value or cell is the 20th percentile. For our example, we get 2.2. So the 20th percentile is between cell 2 and 3, 2 and 2.2 meters. Since we only use the tenths digit, we will use 2.1 as our 20th percentile CBH. So now let's compare the three methods we have used so far. You can see that the canopy base height was estimated as 4.2 meters using the average crown base height, 1.9 meters using the lowest crown base height, and 2.1 meters using the lowest 20th percentile crown base height. This is a fairly large range of values that can change model predictions quite a bit. Let's look at a couple more methods before moving on. Another way to estimate canopy base height is the height at which a minimum bulk density of fine fuels is reached. Here is a vertical fuel profile. We will develop these later in this lecture. We will use this approach along with Sandow and Wick 1972, which suggest that the canopy base height is the height at which a minimum bulk density of fine fuel, 100 pounds per acre per feet, or 0.037 kilograms per meter cubed, is found. By looking at our graph, you can see that using their definition, we never have enough canopy fuel to estimate a canopy base height. So let's use the definition that the Fire and Fuels extension to FVS uses. This definition states that canopy base height is equal to the height at which a minimum bulk density of fine fuel, 30 pounds per acre per foot, or 0.011 kilograms per meter cubed, is found. Using this approach, we would estimate the canopy base height at about 4.3 meters, as shown here with a red line. The Sandow and Wick's 1972 definition could not provide us an estimate in this stand, while the method used by FFE-FVS provided a similar estimate as the average crown base height for this stand. Another method to calculate the canopy base height is to use allometric equations similar to those we used for canopy loadings. Cruz et al. 2003 developed allometric equations to predict the canopy base height for 4 different species: Douglas fir, ponderosa pine, mixed conifer, and lodgepole pine. To use these equations, you need to know the stand height in meters and the basal area in meters squared per hectare. Let's use this equation and see what canopy base height is predicted for our stand. We need stand height and basal area to use the Cruz et al. Equation. If you recall in the last lecture, we calculated the basal area for the stand to be 33.2 meters squared per hectare, so we will not go over this calculation again. We also need to estimate the stand height, and for this we will use the average tree height. Now we can plug in these variables to the ponderosa pine equation and get a canopy base height of 7.2 meters. Here are the 6 estimates we used for canopy base height. As you can see, these estimates ranged from NA using the Sandow and Wick 1972 method to 7.2 meters from the allometric equations, and the lowest estimate of 1.9 using the lowest crown base height. Let's look and see what effects these different estimates of canopy base height will have on predicted fire behavior. Here is a Nexus printout comparing 4 of our estimates for canopy base height. Scenario A is the 20th percentile crown base height estimate. Scenario B is the average canopy base height estimate. Scenario C is the canopy bulk density equal to 0.011 kilograms per meter cubed estimate. And Scenario D is the estimate from the Cruz et al. 2003 equations. For each of these scenarios, we held all input variables constant except canopy base height. The first difference you will notice is that Scenario A is predicted to have a passive crown fire, while the other 3 scenarios were predicted to have a surface fire. Due to this, the surface fire spread rate, fire line intensity, and flame lengths were all predicted to be higher for this scenario. In addition to changes in these variables, the torching index was lower in Scenario A compared to the other scenarios. The torching index is the 20-foot wind speed required to promote a surface fire into the canopy. Notice that this variable is twice as high in scenarios B and C and over 3 times higher in Scenario D than in Scenario A. As you can see, our estimate of the canopy base height could have major impacts on our management recommendations and actions. We will now go over using fuel photo guides to estimate multiple canopy fuel loading characteristics. A stereo photo guide for estimating canopy fuel characteristics in conifer stands was developed by Scott and Reinhardt 2005. This photo guide can be used to estimate the canopy base height, canopy bulk density, canopy fuel loading, stand height, canopy cover, as well as other canopy characteristics. The canopy fuels data in the photo guide was estimated on a single fixed radius plot on 5 study sites throughout the interior western U.S. Although this guide is not very extensive, there is little information available you may find useful. The authors suggest that the guide does not contain enough data points to be the sole basis for estimating canopy cover. For the purpose of this class, we will consider the use of this field guide as a tool to roughly estimate the canopy characteristics of a stand. For each stand type, the photo guide will have 2 pages associated with it. On the first page, you will see a stereo photo pair, a hemispherical photo, and a canopy fuel profile. On the second page, you will see a stem diameter distribution graph and the stand and canopy fuels data for this site. Just as a reminder of the stats we covered last lesson, most stem diameter distributions, as seen here, have left-skewed distributions. In the stand and canopy fuel data, you will notice that this table provides many of the key characteristics we would need to estimate to run a fire behavior model. In particular, you will notice that the photo guide allows you to estimate the canopy fuel loading, the canopy base height, and the canopy fuel bulk density. There are 2 other ways to use these fuel photo guides. Instead of taking the canopy fuel characteristics directly from the guide, you can use it to give you an estimate of the basal area and use the allometric equations we have previously talked about to calculate the loadings. Or you can get the estimates of canopy base height, tree height, and canopy biomass, and then use other equations to estimate bulk density from these. We've covered a lot of material so far, so let's take some time for a short review. Question 1. What are 3 ways you can estimate canopy base height? Question 2. Why is it important to consider the equation you are using to make these calculations? Question 3. What is one limitation of using stereo photo guides for estimating canopy fuel? You can see the notes page for the answers to these 3 review questions. Take a breather. This is a long presentation. Have a little cold warmed coffee, and let's move on to canopy bulk density estimates. One way to estimate canopy bulk density is to use your estimates of available canopy biomass and divide it by the volume. Remember, the canopy bulk density is the dry weight of the available canopy fuel per unit of canopy volume. This volume includes not only the space occupied by the canopy fuels, but also the space not occupied by the fuels. In this lecture, we are going to look at several indirect methods of computing canopy bulk density. These methods can be divided into 4 broad categories: the load over depth methods, maximum running mean methods, lookup tables, and regressions. The concept behind the load over depth method is straightforward. You simply divide the available fuel loading by the canopy depth. This method ultimately assumes that there is a uniform vertical distribution of fuels within a forest canopy. We will cover 3 methods to calculate the canopy depth. Ultimately, our comparisons of these methods will assume that the same method of estimating the available canopy fuel loading was used. For this example, we are going to stick with our 150 10-inch trees per acre in northern Arizona. For this example, we will assume that these trees were measured on a 1/15 acre plot. Thus, we had 10 trees on the plot. This table shows the DBH height and crown base height for the 10 sampled trees in our stand. One method of estimating the mean crown length is called the canopy depth method. In this method, crown length is the difference between tree height and crown base height. This table shows the mean value for each column and the crown length for each tree. Note that their numbers have some error due to rounding in the calculations. After filling in the table, our average crown length is 44 feet. To get canopy bulk density from the mean crown length method, you simply divide the available fuel loading by the depth. In this case, we would have an estimate of 0.03 tons per acre foot. We will now convert this to units that are more commonly used. First, let's get to pound per acre foot by multiplying by 0.0459. Next, let's multiply by 16.01846 to convert to kilograms per cubic meter. And 0.0221 kilograms per meter cubed is the estimated canopy bulk density using the mean crown length method. A second method for estimating the canopy depth is using the height percentile method. In this method, the depth is estimated as the difference between the 90th percentile tree height and the median crown base height. In this table, you can see I have recorded the tree list from the lowest to highest in terms of crown base height. In this case, we need to average 11 and 12 to get the median value, which is 11.5. The next step we need to do is calculate the 90th percentile tree height. To do this, you simply need to rearrange the tree list again such that the trees are from lowest to highest in terms of tree height, and then find the 90th percentile. For our data set, this is the 9th tree from the top. When we do this, we get 57 feet for the tree height. To calculate our crown length, we simply subtract the median crown base height from the 90th percentile crown height, and we get 35.5 feet. Next, we can divide our available fuel loading by the canopy depth and convert to kilograms per meter cubed, similar to before, and we get 0.0232. The final method we will cover is the biomass percentile method. In this method, the depth is estimated as the difference between the heights that 90% and 10% of the canopy biomass occurs. This method requires the user to create a canopy fuel profile. This process can be computationally complex depending upon your assumptions. This method is used in several popular models, including FVS and FMAP. In the right-hand side of this picture, see a theoretical stand. On the left-hand side of the picture, you can see the vertical canopy profile for this stand. We are now going to go over how to develop a vertical canopy fuel profile. As usual, I will use the ponderosa pine stand from northern Arizona. If you remember, we estimated the available canopy fuels per tree at 19.4 pounds in the previous lecture. If we multiply this value by 15, we will have an estimated pounds per acre of available fuel loading. Next, we want to calculate a bulk density for each tree in pound per acre foot. To do this, we simply divide the available canopy fuel loading of each tree by the crown length. Now let's make an assumption about how the fuels are distributed within the crown of a tree. In our example, we are going to assume that fuels are distributed homogeneously throughout the tree crown depth. Note that this method assumes the amount of fuel present at a height is independent of the volume at a given height. This doesn't take into account the cone-like nature of many coniferous trees or other differences that may actually occur throughout the length of the crown. Given our last assumption, we can simply apply our calculated crown bulk density for each tree for every 1 foot section in which there is crown present. To do this, we will set up an Excel spreadsheet which has the tree number followed by the CVD, followed by a column with every 1 foot section listed. For example, 0 to 1, 1 to 2, 2 to 3, etc. This is an example of what my table looks like. Next, we want to fill in the table. For tree 1, we have no crown until 9 feet because this was the crown base height. So at 9 feet to 55 feet, you will enter 6.3 into your form. You will do this for each tree in your data set. You then sum along each column to get the bulk density for each foot in the canopy. After we have the total biomass per tree, it is typically expressed in pounds per feet cubed. So divide by 43,560. Next, we must determine where 10% and 90% of the available fuels are in terms of height. First, we determine the 10% and 90% total fuel loading values. Then compare it to where you observed these loadings. Here is how I set it up. You are trying to find at what height do you have a fuel loading of 287, and we see that it is closest to 14 feet, but somewhere in between 14 and 15. In Excel, you can use the equals sum function, highlighting all values up to that height, which are the values in the last row. For example, the value below 14 is all values from height 14 and below summed. See the Excel example included in this lecture section on BBLearn. In the full expanded table, we would also see the 90th percentile. In our example, there is less than 10% of the fuels under 14 feet and less than 90% under 50 feet. So our canopy depth is about 36 feet. Thus, our estimates is about 0.0285 kilograms per cubic meter. In our example, we made several assumptions about the geometry of tree crowns and the distribution of canopy fuels. You can use the same process we just used, but make different assumptions. However, these assumptions complicate the calculations. Just keep in mind that this is an option available to you. Another common estimate for stand level canopy bulk density is to use the maximum running mean of the canopy bulk density. To calculate a running mean, you first have to decide how big of a window to use. We will not go into the calculations of this, but it is fairly simple. Average the loadings across the distance you have specified. For example, if you had a 3-foot resolution, you would calculate the average of the column of interest, the one after it, and the one before it. You would do this for all the columns, then simply find the maximum value. Another method is to use allometric equations like we discussed last lecture. In the method we just discussed, we calculated the available canopy fuel loading, then the canopy bulk density. We could, however, use allometric equations to directly calculate the canopy bulk density. For this example, we will use the equations developed by Cruz et al. 2003. The Cruz equations require us to know the trees per hectare and the basal area in meters squared per hectare. Note that in the following example, I am using the 150 10-inch trees converted to basal area and tree density in metric units. It is very similar to our previous use of these equations, and we get a canopy bulk density of 0.153 kilograms per meter cubed. Another source of information to estimate canopy bulk density is from lookup tables. An example of a lookup table is those that were developed by Keene et al. 1998-2000, which were used to create the spatial datasets used in FARSIGHT. The lookup tables were developed for a combination of forest type, structural stage, and canopy cover. Within a given forest type, the user must assign a structural stage as either pole, medium, large, seedling, or sapling. In addition, you must estimate the canopy cover for the stand. Based on these estimates, you can get an estimate of the canopy bulk density. The first three methods resulted in very similar bulk densities. However, the allometric equations had bulk densities much higher. To end this lecture, I would like to take a look at the Reinhardt et al. Study that you read. This study is one of the only papers I know of which has attempted to assess the accuracy of these methods. Let's start by looking at the canopy fuel loading estimates. You can see from the results that there was little correlation between either the allometric equations developed by Brown 1977 and 1978 that we covered or the regression equations from Cruz et al. 2003. However, you can see that there is a good fit when the allometric equations were corrected. However, the regression results have a good fit since they were built with this data. So in reality, we would not necessarily expect these methods to produce these results against an independent data set. The results for canopy bulk density are much better. You can see that all of the load over depth methods produced correlations that were above 0.7, and both the biomass percentile and height percentile produce correlations of over 0.9. Lookup tables and allometric equations as implemented by Carlton produced poor results with correlations around 0.55, while the Cruz equations produce results with correlations of about 0.6. Keep this in mind as you choose a method to use on your own data. As we end this lecture, I would like you to think about what method we should use in our analysis. A few things to consider when we choose a method is what variables do we have data for, and can we justify our use of this method? Next lesson, we are going to move on to incorporate all these equations and various fuel strata we have discussed and put them into a fuel model and a fire model.